Okay. One more time. We're going to talk about propagation modes. Basically, Earth, Moon, or moon bounce, meteor scatter, some of the tropospheric stuff, aurora propagation, a little bit about polarization. So let's see. Oh, it worked for one slide.
Pointed at it. Oh, you are.
Yeah. I give up. That's all right.
Which keyboard is plugged into?
This one?
Is it a blue one or a black one?
It's a black one.
Black one.
Okay.
So it wouldn't have gone to sleep that quick.
Well, sometimes USB 2.0 devices don't work well with 3.0. You switch USB ports, it might work.
It seems to work for 2 or 3 slides and quit, or not at all. Okay, so if we remember back, probably from the tech in general about electromagnetic waves and their E fields and magnetic fields at 90-degree angles to one another. And the oscillation, and on other stuff I've read, it's actually the acceleration of the electrons that causes them to actually leave the wire or the antenna and form a wave in space. And that's as far as the physics that I know. We talk about polarization, and we refer to the electric field's orientation to the Earth. So if in the electric field is propagated along the length of the conductor. So if it's a horizontal wire, the E field is going to be horizontal. It's going to go back and forth from one end to the other and propagate perpendicular broadside to the wire. If you rotate that wire 90 degrees, so it's vertical, it's now vertical with respect to the Earth. So it's called vertical polarization. If you have a wave that's, say, partly vertical and partly horizontal, where the horizontal portion is 90 degrees out of phase, it will cause it to rotate in a circle or an ellipse. If they're even, it's a circle, otherwise it's elliptical and it rotates. That's also what happens with a satellite that's rotating. It's generating a rotating pattern, even though it's not, I don't think, truly circularly polarized like the out of phase. But in order to receive it, you normally need cross-polarized antennas, so you see it when it's vertical and you also see it when it's horizontal. So, what is meant by circularly polarized electromagnetic waves? Bravo. Okay, moon bounce. We have a guy in the NASA club that has done this. I don't know that he's doing it very often anymore. It's an expensive proposition. Where you actually bounce a signal off of the moon back to another point on the Earth, somewhere in the same hemisphere. The maximum distance you can go is 12,000 miles, which is like from equator to equator type, assuming that both stations can see the moon. The downside of doing it, I mean, it would seem like it's a nice reflector. It's 250,000 miles away, approximately. And the path to the moon and back is 250 dB loss. So you got to make up for a lot of loss. So normally you got to have arrays. You need a 1500 watt transmitter. You need preamplifiers on the receiver. And then you might hear a little echo. There's there's a typical setup, 16 Yaggies
That's a typical setup.
for somebody that's serious.
I pronounced that the divorce Yagi.
Well, now I think they tend to do it at 70 centimeters or 23 rather than 2. So they don't have to be that big.
And you
Up
can have
there.
them close to the ground.
Yeah, I don't think it matters. But you also need a control to tilt and rotate to track the moon because it moves relative to us. So what's the approximate maximum separation measured along the surface of the Earth between two stations communicating by moon bounce?
D, delta.
But that's true anywhere. That's about the farthest you can talk anywhere on the planet.
No,
No, long path, you go all the way
Well,
around,
I'm
back to
saying
yourself.
The actual distance between points is around 12,000. That's it.
Yeah,
Whether you do it long or short.
well, we'll have to take exception to that and we'll get to it in a bit. Longer than 12.
I'm just saying the physical distance.
Right.
Is about 12.
Okay, the mean Earth moon distance is 248,000, but it varies from 253 to 222. It's farthest at what they call apogee and is closest at perigee. So obviously you have less loss when the moon is at perigee because the distance is shorter. And I don't know what Colombo is, but it just happened to be on the chart I stole off the internet.
Sri Lanka.
Any, huh?
Sri Lanka. I don't know. That's the capital of Sri Lanka.
Oh, it is?
Yeah.
Oh. Okay. Well, I guess maybe they made a contact there. 2 of them, I don't know. So when scheduling moon bounce contacts, which of these conditions will generally result in the least path loss?
Perigee.
Got to remember the difference between perigee and apogee. There's also a thing called libration fading. Now, I always thought libration was wobble on the moon, but according to this text, it's a fading due to the irregular surface of the moon, all the craters and mountains and stuff. So you don't get, it's not a nice smooth surface. And they claim that you can have signal peaks lasting for a couple seconds. Do you know anything about that one, Ernie?
not a damn thing. Never tried it.
That's all I know. I don't understand that, but I'll believe them. So if you happen to stumble onto one of those 2-second peaks, I guess you can better chance of making a short contact.
Well, if you're talking that much loss in that path, maybe a peak makes a big difference.
Well, yeah, a couple dB. It's a couple dB. What characterizes libration fading of an Earth moon Earth signal?
Bravo.
Okay, meteor scatter. Have you done meteor scatter? No.
I just talk to people.
Tonight's the shower.
Are you going to do meteor scatter?
I was
It
tempt-
actually
I was
started, it
tempted
started
to
this
listen.
morning.
Yeah, but I was tempted to just listen as like a, you know,
I've done it on 6 meters from the club
What's that?
station.
I just look.
Oh, you did?
Yep.
Are you sure it was meteor scatter?
That's what Mr. Zari told me.
Well, then it must be true.
was it really quick? Did it fade really quick?
Yeah, it did.
Then it was probably meteor scatter.
The theory says that when the meteor comes through the atmosphere, it leaves this
Ion.
tubular path or cylindrical path behind it. full of ionized material, a lot of free electrons. So that's what you're bouncing the signal off of. Instead of doing it off of the F1 or F2 layer. Supposedly works best in the I guess that's really VHF, right? 28 to 148.
IHF.
No, HF ends at 30.
Yeah, that's 20.
There's a little thing, and they talk about here back and forward reflection. I'm not totally sure I understand that, but it's not on the test. But I guess on forward reflection, you get a longer hop. So when a meteor strikes the Earth's atmosphere, a cylindrical region of free electrons is formed at what layer of the ionosphere?
Somewhere in the F.
E layer.
E layer.
E. Meteor scatters E.
Way up there.
D is just absorption.
Yeah.
D doesn't do anything good, as far as I know.
Absorbs.
It's, well, that's not good.
It could be.
Depends on what you want to do with it.
Well, okay. Which of the following frequency ranges is most suited for meteor scatter communications?
Charlie.
Okay, microwave, tropospheric, and scatter propagation. So, HF normally is not affected by weather conditions, but microwave is. And from what I understand, UHF and VHF are to some extent.
I beg to differ.
Oh, okay.
It seems to me when the storm's coming in and all that kind of stuff, the noise floor goes up dramatically. And you hear all the crackling and snapping when, you know, from lightning strikes away from you.
Yeah.
So.
Yeah, but that's not propagation, that's noise.
Okay. All right. I understand what you're saying.
And, you know, you're right. The noise floor, background noise stuff definitely goes up.
It does knock out microwave during a storm.
One of the things that can affect the propagation is a temperature inversion. So you can actually have a tropospheric duct where you have, see which way does it go?
North, south.
Huh?
It improves.
No, I mean, as far as which layers, I forgot. Cold or on top or hot on top?
Makes no difference.
Oh,
It's just, you have a,
inverted from normal.
yes.
Okay. You can also have atmospheric ducts over bodies of water, like across the ocean or big lakes. Says you can do propagation along weather fronts, warm and cold fronts.
It's the same, top and bottom or left and right.
Okay. Where there's an interface,
Yeah.
a junction,
Junction.
like in a
Like a
semiconductor.
PN junction.
Yeah. The typical range is 100 to 300 miles. Now, I never knew you could do UHF and VHF at those distances.
Yeah, Florida's good for 2 meters for thermal ducting from
When I was
north
in
to
the service,
south.
we had a tropospheric station in Lewes, Delaware. And we would go up 300 miles, 200 to 300 miles. Of course, we had a pretty big antenna,
Yeah.
about 30 feet in diameter and
Yeah.
and 1,000 watts or a couple thousand watts.
Yeah.
I've been able to pick up the Jacksonville repeater from over here in the air.
Really?
With the mobile.
That's
Yeah, there's a repeater on the same,
miles.
Yeah, the same was the N1KSC, right?
up north. And we can hear their input, people on the input frequency, they come in on our input frequency as well.
Yeah, I remember when we did the Space Force run, I was picking up somebody way up north of Daytona.
Right.
Okay, so they claim that it's fairly predictable. There's some websites that you can go to. One of them is William Hepburn's Radio and TV DX Information Center. And he produces Hepburn maps, which is the key. You have to remember what a Hepburn map is. And it predicts the probability of propagation in the troposphere. There's one I took off of his site for, what was that? There's a date somewhere. Oh, it's under the thing. I think it was the 12th or something of October. But they update it every few hours during the day, and you can see it change. And there's a color code that, and I think the orange and red, yellow things are higher probability of propagation. So which type of atmospheric structure can create a path for microwave propagation?
Bravo.
Baker.
Not the jet stream?
We haven't discussed the jet stream, so I would say that's not the answer.
Tropospheric propagation of microwave signals often occurs in association with what phenomenon?
Charlie.
Atmospheric ducts capable of propagating microwave signals often form over what geographic feature?
Charlie.
Does it make any difference whether it's saltwater or freshwater?
I have no idea.
Probably not.
Bravo.
It's the humidity that's doing it, right?
Yeah. What's the typical range for tropospheric propagation of microwave signals?
1 to 300 miles.
Everybody doing Bravo? And what does the Hepburn map predict?
Probability of
Delta.
atmospheric propagation.
Yeah.
Related to Barbara?
Audrey,
Audrey,
or the other one.
Yeah. Good.
What was her? I used to really like her. Okay, aurora propagation. We have these northern and southern lights due to interaction of the stuff coming from the sun with the magnetic fields. And from people that have seen them, with Steve, right? Said he's seen them.
Mm-hmm. You know, when it was based in Alert, Canada.
At night.
Mm-hmm.
You can, because it's a kind of a wall of charged particles, you can bounce signals off of them, both north and south. It does some kind of frequency modulation. So the only thing it's really useful for apparently is CW, because that affects voice signals because of the frequency modulation due to it. So I don't think it's a great way to propagate unless you're doing CW. But CW wouldn't care. I mean, you hear a little warble in the dits and das, wouldn't matter. What's the cause of auroral activity?
Solar winds.
I'm going to say Charlie.
Yeah, it's another one of those E-layer ones. All the sporadic stuff is in the E-layer. Which of these emission modes is best for auroral propagation?
CW.
Alpha.
Okay, apparently during the day, propagation can change quite a bit. So you might have good signals on the upper bands in the afternoon, but they go away at sunset. So you can switch to a lower frequency, and I guess you do a QSY to whoever you're trying to talk to, so they switch.
I was trying to explain that to my wife,
Which,
switching over frequencies. Well, actually, she was asking about, I thought you weren't supposed to talk forever on there. You're supposed to just say hello and then go. And I told her, I said, well, on calling frequencies maybe so, but I said, you exchange some information. If you want to talk more, you QSY to another frequency.
yeah,
And she looked at me and shook her head like this. I said, QSY means change to another frequency. She said, oh, okay.
Just tell her
She's
you're
got to
trying
be a ham before I've
trying to get a
finished.
rag chewer away.
yeah.
That one might take more explanation.
Yeah, it's only the real short things for contesting.
Yeah.
Because we have a lot of people around who like to just talk
Contesting.
And talk.
Mhm,
for a long time.
that's right.
Michael,
Yes, sir.
are you one of those long talkers?
No, not me.
Oh, okay.
I hate to wait for them all to talk before, so I can break in and get a contact and leave again.
Bruce is in here.
Okay, what might help to restore contact when DX signals become too weak to copy across an entire HF band a few hours after sunset?
Go to a low,
Bravo.
lower frequency.
And why?
Because
Because
those
you can't do a
frequencies,
low frequency during the day because
it doesn't ionize.
the D layer absorbs it,
Yeah.
right?
That's mostly.
Because the D
And
layer
there's too
goes
damn
away at
much
night,
noise,
huh?
And there's too damn much noise.
Yeah. Yeah, that comes up a little later in a couple things about the noise. Okay.